All right. So exam 2 is graded. I'm reminded of, well, I don't know if you saw my video on Teams, but I'm reminded of, I don't know why I'm reminded of a scene from The Dark Knight where the Joker and Two-Face are in the hospital, right? And I'm paraphrasing what the Joker would say, but introduce one little X and everybody loses their minds. Because there was a clear enemy on exam 2, and it was the letter X. Because as soon as there's a problem involving algebra, the problem 6 with the functions and whatnot was definitely the kicker. But the good news is that the average on the exam was pretty much exactly the same as the average on exam 1. So you all did very well. But if there's any one piece of advice I would have, it's maybe get a little bit more comfortable with the letter X, because there's going to probably be some algebra on the final as well, okay? And we're not done with the letter X, especially we've got some topics we're going to discuss later on after influence lines, probably during dead week. So just don't be scared of the letter X. Okay, homework 7, I've not yet finished grading that, but I'm hoping to have that graded by Wednesday. The solution is going to be posted on Wednesday, okay? I know there were some students that still had a couple installation issues. If I don't have your homework 7 by Wednesday, the solution's going live, including the Mastan files. So again, there are multiple installations of Mastan in the transportation lab. The actual running of Mastan should be very quick, so like I would get on it. Homework 8.1 is due today. Homework 8.2 is assigned today. That's going to be the second influence lines assignment. A couple of other housekeeping items to close some stuff out. So number 1 is the at-home game. If you've had me for class before, you'll know that near the end of the semester, which, believe it or not, we are near the end of the semester. Can you believe it? There are 41 lectures in this class, and we're on lecture 33. And we're canceling the lecture right before Thanksgiving break. So can you believe it? It's crazy, right? I'm going to post a spreadsheet that I call the at-home game on Teams. I'm going to post it on Teams. I'm not going to post it on Blackboard. And what it is it's a spreadsheet where you can take your homework average, your attendance grade, your exam 1, exam 2, project grade, and it'll figure out what you need to get on the final to get an A or a B or a C or what have you, right? A buddy of mine in grad school called that playing the at-home game. So that's why I call the spreadsheet the at-home game. So I'll post that near the end. The last announcement I want to make is about steel design. How many of you are planning to take steel? I'm just curious. How many of you are planning to take steel and have not yet registered for steel? Okay, I would do so because here's what I'm going to do. After advanced registration, I'm going to send the coupon code to everybody registered for the course, okay, so you can get the manual. But I'm not going to just blast it out, okay? So if you're planning on taking steel design, take it so I know who to send it to, okay? If you remember, I talked about this last time, how there is no textbook in the course, but you do have to buy the manual. And you could buy it on your own, and it's like $360, or you could buy it with my coupon code, and it's $125. But I'm not going to just send it out to everybody. I need to know who's in the class. So if you're planning on taking it, register for it. Sound good? Well, yes, sir. What? Advanced registration starts today.
If you're a junior, it's tonight.
Yeah, it depends on your course, if you're a class registration. If you're listed as a senior, you could register today. If you're listed as a junior, it starts tomorrow. So,
Midnight, which is tomorrow, but it's tonight.
The calendar will say Tuesday. So 12:01. Of course, it's not the engineering classes, right? It's all the math and science classes that you got to get in, right? That's the ones you're worried about. Like I don't know things about stuff. Questions? Okay. All right, let's talk about influence lines. I am curious how you felt the first homework assignment went. I'm actually wanting to ask you before we begin. Was it difficult? Was it easy? How does everybody feel about it? Does everybody feel like they understood that? Okay, good. Because I'm going to take the notion that you understand that homework assignment We're going to ratchet it up a little bit, okay? Because today we're going to do influence lines for internal response, and you kind of need to understand what's going on here. This is kind of important, something to pay attention to. All right, let's recall the Mueller-Breslau principle. That's the technique that we're using to construct an influence line. Remember, all an influence line is a diagram that records the response at a point of interest when a single 1 kip load moves across the structure. And I don't care what graphical techniques or response or any which way or other that you want to construct it, that's the definition. Now, the Mueller-Breslau principle is a shortcut. It's a way of constructing an influence line very quickly and very efficiently. For determinate structures, you can get a quantitative influence line. For indeterminate structures, all Mueller-Breslau will give you is a qualitative influence line unless you actually go through and do the deflections, but that's another story for another day. So how does the Mueller-Breslau principle work? First thing you got to do is you got to identify a response of interest, like what are you drawing the influence line for? The facts are, for us in this course, that's not really a step we need to do more often than not, because I'm giving you a homework problem that says draw the influence lines for the reactions here, draw the influence line for the shear and moment here. So there's no really step one, because I'm doing that for you. I'm telling you, I want the influence line here, or I want the influence line there. What you need to do is remove from the structure the ability to resist that response. Remove the reaction. If it's moment, you insert a hinge at that location, and we'll talk a little bit more about that today. And then you move that structure through a unit deformation at that point, and the resulting deflected shape is the influence line. And so when we did influence lines for reactions, this is kind of what we did. And I gave you 2 homework problems. One of them was, I'd say, simple, and one of them was maybe not so simple. Is that a fair way of looking at it? One of them was a little bit more involved. But there are some patterns that we recognize for influence lines for reactions. So, for example, for reactions, we knew that the influence lines equaled 1 at the reaction of interest, and 0 at all other reactions. So if I look at the influence line, let's say for the reaction at B, it's 0 at A, 0 at C, but it's 1 at B. Okay? They're always linear. They are influence lines. They are linear. And internal hinges serve to change the slope of the line. Okay? So this beam is comprised of sort of 2 rigid links. Even though we're dealing with deformable structures, because we're removing responses, we're creating unstable mechanisms, so they act like rigid links. So this beam is comprised of 2 rigid links. So the influence lines for all 3 of these are bilinear, right? 1 line, 2 lines, 1 line, 2 line, and even this one is 1 line, 2 lines. And the change in slope, the place where the influence line kinks, if you will, and changes slope is at the hinge. Does that make sense? Now, these patterns, and I want everybody to listen to the words coming out of my mouth. These patterns hold true for reaction influence lines. We're going to be talking about shear and moment influence lines here in a second. And these patterns are not necessarily the same, okay? So you got to make sure you recognize that. The one thing that is true is that they're going to be lines, okay? But this whole thing right here is not, like for example, this point 1 is not true for influence lines for internal shears and moments. Just right off the bat, okay? Everybody with me on that? Okay. Let's talk about influence lines for internal shears and moments. So like before, we have to pick a spot of interest, okay? So let's say I have a simply supported beam, and I'm drawing the influence line for the internal shear and the internal moment at a particular point. So this is a simply supported beam, A and B, and I'm drawing an influence line at this section. So I could call it section 1-1. I could say I want to draw the influence line at point C, or this is point D. It doesn't matter. The book sometimes uses C and denotes the spot with letters. I usually do section cuts. It doesn't matter. Now, here is what some of these influence lines are going to look like qualitatively. So this is the influence line for the shear at that section. This is sort of what it looks like, and we'll talk about how to construct this here in a bit. Okay, so here's the influence line for the shear at section 1-1. What's going to happen is the left side is going to tend to deflect downward. The right side is going to tend to deflect upwards. It's not always the case that one side deflects down and one side deflects up. Maybe only one side deflects up or only one side deflects down. But if you have two different changes, the left side's always going down, the right side's always going up. And that owes to our sign convention. Now, I'm curious if you all have been paying attention. If I were to take a ruler and measure the length of this line right here, what do you think that measurement's going to be? How long do you think that jump is? Oh, well, not quite, because the load's moving. And, well, let me ask this way. How much load are we moving? One, okay? I propose that this jump is always going to be a jump of 1, okay? So, for example, just to put some numbers on this, okay? If this is negative, here, let me move my keyboard here. If this is, I don't know, negative 0.32, just to put a value on this point right here, then this point right here is going to be positive 0.68, okay? That total jump is always going to be 1, right? If this is positive 0.75, this is 25, right? If this is a half, negative a half. If this is 0, that is 1, okay? The jump is always 1 because that's the magnitude of the load that we're moving across the structure. Does that make sense? Everybody okay with that? Okay, so that's just something to keep in mind. Okay, now that's what an influence line for shear looks like. Here's what an influence line for moment looks like. Okay, now I will go ahead and tell you that this point right here is not going to be a magnitude of 1. In fact, it's probably going to be something different. It might be a magnitude of 15 or 2.6 or whatever. But how we determine this magnitude, just like how we determine how much this is and how much that is going to be the focus of today's lecture. Okay? Now, just so you are aware, the only drawback to drawing influence lines for internal shears and moments is that you can only draw an influence line for one point at a time, right? I can draw an influence line right here and get the response. So to be clear, taking this influence line or this influence line doesn't really matter. This influence line tells you what the moment is at this point when the load is anywhere. Like the load can be anywhere on the structure, and this influence line is telling me what the moment is right there. So if I can only draw the influence line at one point of the structure at a time, maybe the question is how many points are enough, okay? I mean, how many influence lines do I need to draw as an engineer to fully encapsulate the structure? Well, common practice among bridge engineers is to draw influence lines at every 10th point along the span. That's very common in bridge engineering applications. So if I have a 60-foot bridge, I will draw influence lines every 6 feet. I will draw an influence line for the internal response at 6 feet, at 12, 18, 24, so on and so forth. And that is usually enough to fully categorize the envelope of loads that a bridge could experience. And you're like, what's an envelope of loads? We'll get to that, okay? Again, we will get to that later. Okay, now, before we review the rules for influence lines, for internal shears and moments, we need to go back to our sign conventions, okay? Internal response influence lines, they follow the sign convention that we've been adopting this entire semester. There's nothing different. So when you cut a section, remember when you cut a section and you look to the left, we say downward shears are positive. And when you cut a section and look to the right, we say upward shears are positive. Do you remember that? So whenever we draw an influence line, let me go back to this. So here's the influence line for shear. The left side went down, the right side went up. That's because, according to our sign convention, the left side goes down, the right side goes up. So that's why our influence lines for shears look the way they do. For moments, what happens with moments is this is our sign convention that we've been using, right? So whenever we cut a section and look to the left, that's what the moments look like. cut a section, look to the right. That's what moments look like. When I say that's what moments look like, I mean those are what positive moments look like. So look at what's happening with the moments right here. If here's my point, they both serve to sort of rotate it up like that. Y'all see that? So here's the influence line. They're both rotated up. Does that make sense? Okay. Okay. Let's talk about these one at a time. Let's get into some details. This is kind of important. Okay. Let's look at the influence lines for drawing for internal shears. Okay. So we go to the Mueller-Breslau principle. We release from the structure the ability to resist shear at the point of interest. So what that means analytically is we institute a shear release. Okay. Now we've never dealt with shear releases before in here. This is the first time and really only time we'll deal with them in structural analysis. But the long story short is that a shear release releases the ability to resist shear, but not the ability to resist moment. So I could take that section and bend it, but I can't shear it. It'll just freely displace. Okay. Now, what that means is this, and you'll understand what that means when we look at the final shape here in a second. So I release from the structure the ability to resist shear, and then I move that point through a unit displacement. Now, what that unit displacement typically means is that the left side tends downward, the right side tends upward, and by golly gosh gee, there's my influence line. And I propose that that total jump is 1, right? With me so far? Now, that total jump is 1, but that doesn't tell us how to determine the size of those jumps, right? This might be 0.4, negative 0.4, and this might be positive 0.6. This might be negative 0.8, positive 0.2. How do we determine the size of those jumps? Well, if you recall, what I said is that this is a shear release, not a moment release. So we have to release the shear while at the same time attaining moment equilibrium. And the way that we attain moment equilibrium is that in order to release the shear and not the moment, these two lines have to be at the same slope. Okay? So when we construct our influence line, we know that this height plus this height equals 1, and we know that this slope ratio, h1 to this length, equals h2 to this length. And so once we've got that, we can solve for one of our heights very easily. And then the rest is just plug and chug and slope ratios. And don't worry, we got an example we're going to do here in a bit. This is actually really, really easy. Okay, with me so far? Okay, this is shear influence lines. Now let's look at moment. Now with moment, we identify a point of interest and we remove from the structure the ability to resist moment. Now that one's easy. We install a hinge. Okay. So whenever we're drawing an influence line for moment, we place an internal hinge at the point in question. We then move that point through a unit deformation, but because we're talking about moments, we move it through a unit rotation. Okay. So what a unit rotation means is that I rotate this up a little bit and I rotate this up a little bit. And when I say unit rotation, what I'm saying is that the slope of this line plus the slope of this line has to equal 1. Okay? So the slope of these two lines has to equal 1. The slope of this line is rise over run, h over L1. The slope of this line, rise over run, h over L2. So h over L1 plus h over L2 is 1. I can easily solve for h. Okay? Does that make sense? Don't worry. We're going to go through, I'm not going to just say, oh, here you go, good luck. We're going to go do some examples. Well, yes, but you're solving for the height so that doesn't happen. Don't worry. You'll just follow along with it. I promise I will make it easy for you. Any questions? All right, so here's the summary. If you want to, hey, here it is, summary slide. This is a nice little summary slide. So this is the expression for shear influence lines that we can derive. If you want to plug and chug, you can. I find it easier to just look at the influence lines and know the patterns. This is the expression for shear influence lines. This is the expression for moment influence lines. Now, like I said, the patterns are different, okay? What do I mean by the patterns? Influence lines for internal response will always equal 0 at all of the reactions. Here's this beam. Here's this table. If I'm sitting right here on the leg of the table, how much internal response is right here? Nothing, right? Because I'm focusing all of my load on the leg. The table isn't seeing anything, right? It's only until the load actually starts acting on the table that I generate internal response in the beam. If the unit load is over the reaction, the beam experiences no load. They're always linear. And again, internal hinges serve to change the slope of the line. So, for example, with this beam, if I do the moment influence line, I put a hinge here, 2 rigid links, 2 lines. Does that make sense? Let's do some examples. I think the easiest way to understand this is to do some examples. Now, if you remember, we're going to do example 1 and example 2. We already did these examples. We did the reactions. Now we're going to do the influence lines for internal shear and moment. For this first one, you're going to do internal shear and moment right here. Next one, internal shear and moment right here. So let's see what happens. The dean is calling me. Give me 1 second. I will say I'm in class. All right, so let me pull this up. Okay, so here's the influence line for example 1. Okay, here's the influence line for the reaction at A. Here's the influence line for the reaction at C. Is everybody okay with that? Hopefully that should have been pretty simple. Okay. Now let's do the influence line for the shear at B, the influence line for the moment at B. Now, for both of these influence lines, the value for both of these influence lines is going to be 0 at the supports. Okay? It's going to cross through 0 at the supports. If I put a load directly at point C, there is nothing going on inside that beam, period. If I put a load at point A, there's nothing going on inside that beam, period. Does that make sense? Now let's do the shear influence line first. Okay? So the shear influence line, what I'm doing is I'm installing that shear release at point B, and I am deforming it in such a way that the left side goes down, the right side goes up. But I am doing that in such a way that the slope of those 2 lines are the same. So I propose that that the influence line probably looks something like this. Oh. And probably something like this. That's probably the influence line right there. Boom, boom, boom. There's your influence line. Does that make sense? The shape. I'm not talking about the values. Let's just talk about the shape. And if it doesn't, please stop and go, Dr. Mike, what the heck's going on? Everybody good? Now, what we need to determine are a couple things. First off, we need to determine, we'll call this H1, H2. We know this value is 0, this value is 0. And we also need to call this. We'll call this V at D. Now, why am I calling this something different? Because once you get H1 and H2, the rest of the influence line comes from slope ratios. Okay? The rest of it just comes from the slope ratios. Let me ask you a question. Numerically, what do you think this is? If this is H2, H2 is to 10, as something is to 10. That's just H2, right? It's just negative H2 because it's going downward. Does that make sense? Okay, so how do we determine these values? Well, so we use similar slope ratios. I propose that H1 is to 20 as H2 is to 10. Same slope. So equation 1 is that. Is that okay? And so maybe what I ought to do is just make sure that what we're talking about here is that height, so that we're not having to deal with positives and negatives. We'll let the context figure that out. Now, if everybody's okay with that, help me out with this. What does H1 plus H2 equal? What's that? Well, we're going to get to that here. Here, I know what you're talking about. But just in general, what does H1 plus H2 equal? 1. Now, you got to do the substitution correctly. H1 is 2H2. So you said 3H1, it's 3H2. So what is H2 now? And if H2 is a third, what is H1? 2/3. So I propose that this is negative 2/3, this is positive 1/3. And if this is positive 1/3, what's that value right here? Negative 1/3. Boom. There's your influence line for the shear at B. We're going to stop for a second, see if that makes sense. This is new, this is weird, I know, which is why we're going to take our time with it. What do we think? Any questions? All right, now, the moment at B. Let me erase this stuff up here. So what we do is we insert a hinge at B, okay? So we are placing an internal hinge. We are rotating that upward such that that total slope is 1. So this side is going to go up like that, okay? So that's what that side's going to do. Okay? Tell me what's going to happen on this side. Are we going to go down like that? Why? Has to go through 0 here, so what's it going to do? Like that? That's exactly right. Boom. Okay, there's the influence line for the moment at B. It's that simple. 0 and 0. And again, what we got to determine is this height. Oh. Now, actually, let me use a different color for that. Let's use green for that. Now, the way that we determine this height is a little different than how we do it for shear, but it's also a lot easier, okay? This height here, we'll call this, hold on. This height here, we'll call this MD, although it's pretty easy to figure out. Okay. The way that we determine moment influence line values is a little easier because I propose that this slope plus this slope has to equal 1. So we'll call this right here slope 1, call this line here, or this line right here, slope 2. So slope 1 plus slope 2 is 1. How do we express the slope of this line? I'm asking. I want somebody to tell me. What's the slope of that line?
H over 20.
H over 20, right? What's the slope of the second line?
H over 10.
H over 10. So H over 20 plus H over 10 is 1. Ooh, letter X, although it's called H now. Algebra all over again. What do we do? H over 20 plus 2H over 20 is 1. 3H over 20 is 1. H is 20 over 3. Is that right? How'd I do? Right? Put that in common denominator, add them up, flip and multiply. What?
Do we need to subtract it because it's a negative slope or slope 2?
No, I get what you're saying. I get what you're saying. But the idea is that the total rotation equals 1, and both of those rotations follow positive sign convention because this one goes that way and that one goes this way. That's a very fair question. But it's because the internal rotation followed positive sign convention. That's a very good question. What do we think? So this point right here is 20/3 or 6.67. If this is 6.67, what's this point right here? Negative 6.67. All right, I want to stop for a second. I want to see, does this make sense? I don't want to just barrel through this, okay? I want this to make sense. Is everybody okay with this? Again, so for shear, the two lines have to have the same slope, and that the sum of those two heights equals 1. So two equations, two unknowns that you can substitute and solve. For the moment, that slope and that slope have to add up to be 1, so there's actually a lot less to solve. Sound good? Let's make it a little more funky. Let's look at this one. Remember this one. We did the reaction influence lines. Now we're going to do shear and moment. I'm going to give you a sec to copy this down because I want you to pay attention to what we're doing. I don't want that part to be a problem. So just so you are aware, we're doing the influence line. Here, I'll put this down. We're doing the influence line for the shear at section 1, 1, and the moment at section 1-1. One of the other things that does help when you're drawing influence lines, in addition to having a straight edge, is to actually try and draw them to scale. Because if you're drawing them to scale, according to the rules, it can actually help illuminate what the values should be. And so when you do the math at the end of the day, you go, oh, it actually matched what I thought it was going to be. And that, my piece of advice right there is particularly true about shear influence lines. You'll see that here in a second. I'll give you a sec. We got plenty of time. I don't want to hurry this. I still see some folks writing some stuff down. I told you I was going to take your understanding of structural analysis and turn it upside down and flip it inside out and turn it into a pretzel, you know. All right. Is everybody at a point where we can start doing this, or do you need a little bit more time? Okay. Let's look at the influence line for the shear at 1-1. What is the value at A?
Here.
What's the value at B?
Here.
What's the value at C? Before we begin, you better have that part right, okay? So 0, 0, 0. Is the same thing true on the influence line below? Yes, 100%. 0, 0, 0. So before we even put, ruler to paper, straight edge to paper, and actually drawing this stuff out, that should be known, okay? All right, now let's see if we can construct this influence line. Let's start off with shear. We are going to institute a shear release. Left side's going to go down, right side's going to go up. Now before we start drawing stuff, let's use our noggins a little bit. If I take that beam at point 1, and I break out my samurai sword or lightsaber if I'm a sci-fi fan, and I slice that beam in half right at point 1, how many rigid lengths is this beam going to be split into? Say it again? 3, right? There's the rigid length from A to the hinge, from the hinge to the cut, from the cut to C, right? So how many straight line segments should I have? 3. So if I take the now I want to focus on the central segment. The central segment from the hinge to the cut. So if I take that left side and move it down, does it go like that? Why? Has to be 0 at the hinge. So maybe like that, right? And so if that goes like that, then this is going to go up. Is that a fair statement? So, okay, all right, hold on. So what you're telling me then is that the influence line goes, wait, hold on. Sort of goes, I don't know, like this. Oh, my line, my thunder's getting stolen by OneNote here. Why is it not liking the object snap right there? It does not like my object snap right there. I do not like that. I'm going to undo that. I'm going to see if I can fix that object snap a little bit. There we go. That's going to bug me if I don't get that right. So that one needs to go like that. It's like you have to hover with it and then it stops snapping. Now I've tried desperately to find object snap settings and I cannot. So would you agree with that so far? And so the right side needs to go up like this, right? Now, remember what I said at the same scale? I'm going to try and draw this line going up, but I'm going to try and do it at the same slope. Let's see if I can do that. So, all right, hold on. So this needs to go like that. And what do you think? Something like, how'd I do? Is that like the same slope? This line and this line, are they at the same slope? Kinda. So, would you agree that, so first off, that's our influence line, and we need to find H1 and H2. Now, I took great care to draw this at scale, which, hold on, by the way, let's also denote the values that we know, right? This is 0, 0, 0. Drawing this to scale, what can you tell me about H1 and H2? What? But, yeah, that's true when you sum them up, but to scale. Which one's bigger? H1's bigger, right? By drawing it to scale. Now let's see if the math bears that out. So let's look at shear influence line values. Actually, let me move this up a little bit. So H1 is to what as H2 is to what? What's the slope of this line? H1 is to what? 14. What about this line right here? H2 is to what? 6. So H1 is to 14 as H2 is to 6. So H1 is 14 over 6 H2. Did I do that right? How'd I do? Now, as Mr. Adams put, H1 plus H2 does in fact equal 1. So instead of H2, I'm going to do, or sorry, instead of H1, I'm going to substitute 7/3 H2. Did I do that right? Right? H1 is this. So instead of H1, I put that. So if I have 7/3 H2 plus H2, how much H2 do I have? 10/3. So 10/3 H2. Oh, I'm veering. What's H2? 3 over 10. And if H2 is 3/10, what's H1? 7/10. So applying my signs, this is negative 0.7. This is plus 0.3. See what I meant by drawing it to scale? We found that H1 should be bigger, and in fact it was. Now, we're missing a value, aren't we? We're missing this one. How do we determine that? Well, let's see. We need to determine this height right here, let's call it height at the hinge. Anybody know how we're going to determine that height? Using H1, exactly. Because H1 is to 14 as something is to 8, right? It's just a line. So H1 is to 14 as H1 of the hinge, or H of the hinge is to 8. So therefore, what is 8 over 14 times 0.7? Say it again. 0.4. Do I have a second on that? That's the influence line for shear at section 1-1. Now, I don't want to barrel through this. Is this making sense? Now, we're going to real quickly do the moment at section 1-1, but is everybody clear on this? Okay, so watch what we're going to do. Everybody pay attention. We are going to insert a hinge at section 1-1. That is going to create 3 rigid segments, okay? The side to the left goes like this, the side to the right goes like that, and then we have to go through the hinge. So we're going to have 1, 2, 3. That's going to be our line, okay? So one, 2, 3. Line there, line there. 0, 0, 0. What we've got to find is this H first, then we got to find this one, which is, again, a height at the hinge. Now, the way that we're going to do that, and I know I'll probably get close to running out of time, but I'll do this pretty quickly. Is with moment, the math is actually a lot easier. This height needs to be that magic height so that the slope of this line and the slope of this line is 1. So this is slope 1. This is slope 2. So slope 1 plus slope 2 is 1. Slope 1 is h over 14 plus, in this case, is h over 6. And so what I'm going to do is I'm going to use common denominators, right? So for this first one, I'm going to do 6h over 14 times 6 equals 14h over 14 times 6 is 1, or sorry, plus. And so 20h over 14 times 6 is 1. H is 14 times 6 over 20. 14 times 6. And so in this case, when you chug that out, you're going to get an H of 4.2. So that's going to be plus 4.2 right there on the influence line. And so the only thing left to do is to use the slope ratio here to determine the remaining height. So H is to 14 as H hinge is to 8, just like we did before with the shear influence line. H hinge is 8 over 14. In this case, it's 4.2. So when you chug that out, you get a value of 2.4. So this value here is negative 2.4. Let me clean that up a little bit. That one's a little weird, isn't it? Again, we haven't actually started using these influence lines yet. We will. Right now, I just want you to be comfortable with constructing them. Here, I'll put a little line through this in the notes so that you know it's a different calculation. Put a little line through this so you know it's a different calculation. Let me stop for a sec, and then we're obviously done. But does anybody have any questions? 2 more problems on the homework assignment. I want to see what you can construct, okay? Everybody good? That's all I've got, everybody. I will see you all on Wednesday.